Alrighty, morning everybody. Welcome back on this lovely day, Calc 2. Plan for today is we're going to finish off our discussion of Standard 2, talking through some more examples of use substitution, as well as talking about how you adapt use substitution when you're looking at definite integrals, as opposed to indefinite integrals. As far as office hours go, due to the weather, I decided to change my office hours around for the next couple days. Decided to go, because we're supposed to get something like up to 8 inches of snow by the end of today, I decided I'm going to cancel my office hours and head out after my last morning class. So I'm canceling my office hours for today, but instead I've decided I'll hold, since a time slot just opened up, I'll hold an extra hour and a half of office hours tomorrow morning. So, of office hours tomorrow morning from 10 to 11:30, as well as the usual Thursday office hour from 1 to 2, but none today. I apologize for that, especially if you were planning to come meet with me today, and you can't make it to my office hours tomorrow, send me an email. I'd be able to make something else work out for tomorrow. If you had already scheduled a retest with me for today, my apologies. Let's reschedule that. But we'll make something work. As far as homework goes, though, I did post another web work, homework 3, which will be due on Monday. And we're also going to have a quiz on Friday over Standard 2. As well, don't forget you have 2 homework assignments, homework 1 due tonight, and homework 2 due Friday night. Again, those are on web work, passed out instructions, and they're also posted on Canvas for how to access the online homework, of course. If you haven't done that yet, you should. Speaking of quizzes, I have quizzes from Monday graded, as well as retests from the last couple days, so go ahead and pass those back. Bear with me, still working on names, especially if you're new and if you're a returning student who's sitting somewhere in the room different than where you did last semester. Prepare for a little bit of disorientation. Mary. Joanna. Anna. Sarah. Reagan. Katie, Kate, Bethany, Phoebe, Christopher. Kayla, Taylor, Joy, Jonah, Aiden, Nathan, Maria, Ty, Emerson, Allie, we get exercising, Nolan, Kate, Nora, James, and Laura. So, you may have noticed you got a letter instead of like any sort of score at the top of your quizzes or anything I passed back. So, a reminder to what those mean. M means you got a mastery. Good job. Pat yourself on the back. You've gotten your first, or for a few of you, your second mastery on Standard 1. From there, J stands for Journeyman. As a reminder, Journeyman means you had a lot of good ideas, you had most of it, but there are some things key that you were still missing somewhere in there. And N is Novice, meaning you still have a ways to go on that standard. You're clearly struggling with that quite a bit. But Dr. Gerstle, I got an M- or a J+ or a J-. What does that mean for my grade? M- is still a mastery. It's worth the same for your grade. J+, J- are worth the same as J, which means you didn't get a mastery. Typically, M- means you did something small that made me slightly displeased with you, but not displeased enough to take away the mastery. It's like you made like a small arithmetic error, you accidentally dropped a negative sign somewhere. That's the sort of thing that would cause you to say, hey, you knew what was going on, you just made a small boo-boo, I'll give you the mastery. But I want to write it M- so you know you made me slightly unhappy. Journeyman, Novice, again, these don't affect your grade in any way. These two. That just means you didn't get the mastery. Again, you're welcome to send me an email to set up an appointment to come in and do a retest outside of class on Standard 1. No, you can't do another one if you've already done your retest for the week. And there will be plenty more opportunities to come in and do retest on Standard 1 as well. So even, for instance, if you've already retested Standard 1 this week, you can come back in next week and retest it again if you still need a mastery on it. And also keep in mind that we will have 3 midterms and a final, all of which will have an opportunity to get a Standard 1 mastery on them. So first quiz didn't go as well as you would have liked. Don't worry, still got plenty more opportunities to get those ends. Any questions or comments about the grading? I've not updated Canvas yet with everyone's mastery totals, considering you all are coming in at all hours of the day to do these retests and earn masteries. I typically will only update Canvas about once a week with everyone's mastery totals, usually on the weekends. So at the end of this week, I'll go into Canvas and input all of your mastery totals, which will be anywhere from 0 to 2 for Standard 1 and potentially up to 1 for Standard 2 from Friday's quiz. And so at the end of each week, you'll be able to go in and know exactly where you stand on mastery total-wise. All right, and with, yes?
So that's a weird question, but did you originally create the system of grading, or did you get it from somewhere else?
Ooh, did I originally create the system of grading, or did I get it from somewhere else? The whole mastery-based grading system in general, I did not create myself. This is something that several disciplines have done for a while, and some disciplines it's called standards-based grading. There's actually a few different names for it. I've kind of tweaked it. So like for instance, I kind of tweaked previous examples that I've seen of this system for requiring, for instance, 2 masteries on every standard. I'm the one who's kind of decided to set what are going to be the different learning standards throughout the semester. So short answer, I'm not the original one to come up with this grading scheme, but I have kind of done a lot of personal adaptations from me having seen it at other places. Anybody else? Why did the yardstick want his parents to stop supporting him financially? Why did his parents stop supporting him financially so that he could stand on his own 3 feet? And with that, let's do some math. So last time we talked about kind of our first new integration technique of the semester, U substitution, which we said we could use to undo one of our differentiation rules from Calc 1. Which differentiation rule did we say u substitution was designed to undo, or to do backwards, so to speak? Phi?
The chain rule.
Yeah, the chain rule. Where the whole idea behind trying to do u substitution is you're sort of replacing what's the inner function, the g of x, from the chain rule, with you're replacing your inner function with like a new dummy variable u that you can use to then integrate with respect to u and make your life a lot easier than trying to integrate with respect to x or with respect to t, or whatever other variable the problem's using. So as a quick reminder, let's do one more of these examples. Let's look at integral. I'm going to be on the fourth page, I think, of the packet. Integral of t e to the negative t squared. Where we have multiple things going on. We have a t, we have e to the negative t squared, and we can't just integrate by taking the integral of t times integral of e to the negative t squared, because A, I don't know how to integrate e to the negative t squared, and B, that would break the product rule. So, how can we make a choice for our u substitution? How can we choose u as an expression in terms of t that'll make integrating this a lot easier? Joy? You look like it.
I was thinking you do negative 2 negative t squared as u.
Let u be negative t squared?
Yeah.
Yeah, I like that idea. We kind of said yesterday, or Monday, that a good choice for you is to sort of take whatever it looks like to be an inside function on your expression. And here, since we're doing this e to the negative t squared looks like an inside function, in that you're taking negative t squared, and then you're taking e to the power of that. So if we do that, we'll get u is equal to negative t squared. So what does that make du dt?
Negative 2t.
Negative 2t, which will tell us that du is negative 2t dt. We break up the du dt as a fraction. And I noticed we don't have a negative 2t dt. We have a t dt. So, Reagan, how can we multiply both sides of this expression by some constant so that on the right-hand side we'll just end up with a t dt instead of a negative 2t dt?
You can multiply by half.
Yeah, we can multiply by a half. I'm going to multiply by negative a half, I think, to cancel out the negative sign as well as the 2. By the way, when you say negative 2t dt, that's a lot of sounds in a row. Fun to say. So with that, I think we can go ahead and integrate this. The t dt becomes a negative 1/2 du. The e to the negative t squared, if u is negative t squared, that's just going to become e to the u. So we're going to end up integrating negative 1/2 e to the u with respect to the variable u. Nolan, what would we get if we integrated negative 1/2 e to the u with respect to u?
Wouldn't it just be negative 1/2 e to the u?
Yeah, it would be negative 1/2 is just a constant multiple, so it comes along for the ride. Integral of e to the u, well, it's like what function has a derivative of e to the u? E to the u. Almost.
C.
plus constant, because we're doing indefinite integral. And as always, the derivative of a constant is 0, so if we're trying to find all the antiderivatives, we need to include that constant term at the end. So, what's going to be our last step? Bethany?
We're gonna substitute u back into this equation, so we'll go -1/2 e to the -t² plus c.
Yeah, since our original integral was written in terms of the variable t, we'd like our final answer to also be written in terms of t. So that's going to give us -1/2 e to the -t², replacing our u with -t² plus c. And I think that is what our integral would come out to be here. So again, when you're trying to choose a u, it's oftentimes helpful to have the u be kind of the innermost function. In this case, when we have multiple things going on, like e to the power of -t², the inner function is the thing you're doing first. You're taking -t² first, and then taking e to the power of that. So having that choice for u can be handy. Any questions, comments, concerns? Groovy. Let's do a spicier one. Using everybody's favorites, trig functions. So if we flip the page, I would like to integrate tangent of x times secant squared x. And we're going to do this in two ways. We're going to first integrate this using a u substitution of u equals tangent of x. And we're also going to integrate this using a substitution of u equals secant x. This is going to be an interesting expression in that both of these u substitutions will actually lead us to an answer. So what I would like for you all to do is to see what happens if you integrate this expression using two different u substitutions, one using u equals tangent x, one using u equals secant x. And then see if you notice anything interesting about your answers that you get using integrating the same function by two different means. So go ahead and take a couple minutes. As always, you're encouraged to work with the people sitting around you, talk to your neighbors, in other words, and see what you can find looking at this integral from a couple different methods. And as a hint, derivative of tangent of x is going to be secant squared x, and the derivative of secant of x is secant x times tangent x. So take a couple minutes, talk to your neighbors, see what you can make of integrating this one function by two different u subs. As always, talk to your neighbors if you have questions, or feel free to flag me down if you would like some tips on this one. sure that, I'm pretty sure you just took an indefinite integral and didn't include a plus c, so yeah, I think it is wrong.
Oh.
You think it's wrong for more reasons
Yeah.
than that?
Yes, I figured out that's not. Just like if you were that and you get that.
Sure you did.
You do? Okay.
Yeah, you did differentiate that.
We just get squared.
You'll get tangent of x times the derivative of tangent of x, which is secant squared,
I
using
gotcha.
integral.
And get squared of x. Let's see. Did you get that? That's what I got. Same thing? Yeah, I got and squared of x. Let's see. Yeah.
But you may be able to make that into something else using combinations, like making it sine squared over cosine squared.
Yeah, I don't know if you need to make that.
What were you saying, David?
I said you might be able to turn the tan squared of x over to into something
So what
else.
would you do for this integral of x?
Intriguing.
You just go, you just like
Are those the same? Did something go wrong?
Look at the bottom question. Yeah.
No, doing okay.
Oh, wait, well you could put both answers and then set them equal to each other to see if you can move it around.
So I think the issue that you have is with your du term. If you let your tangent of x to u, you're gonna be left with secant squared x dx, right? Here you're saying secant squared x dx is just equal to u. So I think if you replace secant squared x times dx with just plain old u using this line right here, you actually just get integral of u d without the secant squared x. Basically, I'm saying all of this right here is going to become your because of what you said. So basically, you can say tangent x becomes u, secant squared x becomes your du. And so really, the integral comes out to integral of u. Does that make sense? And then you can integral u to u. Something that looks a lot easier to integrate than something involving tangents and secants and whatnot. That makes sense.
I just wasn't like, so you can like plug everything in, so like, you're gonna do it in a power.
So let's see.
So right now, that plus one, you're gonna add on to that, right?
Over.
Yeah, I'm gonna do this side of it.
I think there's two copies of secants, right? So I think one of those can be your u, and then another copy of secant can be combined with the tangent and the dx to become your du.
Yeah, squared of x plus secant. There you go, too. Oh, you get, oh, no,
See
you
that?
have.
Would you not? Why don't you go ahead and evaluate this and, so you can get like a final answer and then see if you can do some sort of comparison between them.
So did you get the du being the x?
So for
There's sort of
this
four
one.
trick
So-
features on this one that you can work with and two on this
You have two copies of secant.
because this reduces into like
One of
two
those can be
of
your
signs and then this
Well,
reduces
but
into
one of
two
these copies
signs.
of secant.
So you might be able to like cancel some of the sounds. Like when you go from here to here.
Isn't that?
Yeah. So
I think that's what you have.
So like, you have like.
right, so this is
Really?
secant.
This
This
is
is also
up to,
secant
and
and
we had
secant handed to
tangents, so
you.
that's
So this is technically u times u is
But then
secant times
you-
secant tangent.
So one of them is
Let's write this down.
So I can plug that, and then you have to toggle it. Oh, so it's so you have
So first of all, would you
and
agree
then
that we could rewrite this as
so
an engine
when
that
secant, one of the secants would come
times dx?
and then one of them would be part of the
It looks like
secant.
you're gonna wanna replace your secant x with
So
the,
then back
or
to
one of your secants, doesn't really matter which one.
No, but I.
And it turns out,
So then it's just the same as
to
this.
me, it sounds like du is gonna be equal to secant x times tangent x dx. So I think all of this is just
Yeah, wait.
make this just vanilla.
So this really,
So it really is like integrate, so you end up with something where it's like literally just
Yeah,
integrating like
so
the
secant
simple
squared of
theory.
x equals sine squared of x
And then
over
you can,
cosine squared of
that's,
x.
yeah, take these out. That doesn't make
Yeah, that's
sense.
weird. So then it makes one equal sine squared of x.
Doing alright back here?
like a couple pieces in, like you're trying to find one that fit. And then just trying to get it all.
It got weirder because I set them equal to each other and then reduced it into one equals sine squared of x.
That's generally not true.
Yeah.
Unless x is an odd multiple of pi over 2. So, in general, yeah, secant squared and tangent squared are not the same thing. Tangents, that one's tricky. You could actually do this, we'd be a different use of it, but that's something to do necessarily. Because here I think what you'll get is, if u is tangent x, don't you just want to replace this tangent x with u and not tangent of u? Because tangent of u would be something like tangent of x.
Yeah.
That's what, that was a little sus.
Yeah.
So I think what, I think you just have plain old u, and then the secant squared x dx becomes the du, so you really just get integral du.
Without thinking too.
Which is,
That's something you can reverse power rule.
sure.
Something to think about. Let's give it about one more minute, then we'll come back together and talk about these as a class. Well, then that's a conundrum. How's it going?
Just curious if it boards in and explain the
Yeah. If you're getting different answers, that doesn't sound right, so.
Right.
I will say you integrate, I will say these are both what you should, what I wanted you to get for this semester. So let's come back together and talk about these, because some of you are making some interesting observations I hear as I'm walking around the room. So first of all, if we start by integrating where we let do u sub where u is equal to tangent of x, we would get du dx is going to be secant squared x, so that du becomes secant squared x dx. And when we plug in everything and rewrite our integral in terms of u instead of in terms of x, what does our integral look like? James?
U to U.
U to u. The tangent x becomes u. The secant squared x dx becomes d. So we literally just get the integral of plain old u. So, Joanna, how do we integrate u by itself?
You would just have to use the reverse power over and then u squared over 2.
Yep, we get u squared over 2. I like writing it as 1/2 u squared.
And then it just, I wrote it the other way, but I had tan squared x over 2 plus c.
Yeah, and then plus c. And then if we replace our u's with x's, you're right, we can write that as 1/2 tangent squared x plus c, or tangent squared x over 2 plus c. However you want to write it is totally fine there. So, if we integrate one way, we end up with 1/2 tangent squared x plus c. If we integrate it the other way, though, we can also, I think, try integrating this by making a substitution u equals secant x, which would make du dx equal to secant x tangent x, or equivalently du equal to secant x tangent x dx. So, what do we get if we rewrite this new integral in terms of u? Yes.
U to U.
No, I mean this integral, not the first one.
It's the same thing.
Oh, this one's also u du? Well, we write this as secant x, say, times secant x dx. Hey, this copy of secant x can be our u. Oh, hey, tangent x times secant x times dx. All of this can be our du. Well, what do you know? It's just u du again. Which, well, we already know how to integrate that. That's just 1/2 u squared plus c. And now if we do our substitution, we'll end up with 1/2 secant squared x plus c as our answer. We plug back in our x expression in terms of u. Everyone all right with that? Phoebe, I see you shaking your head. Are you doubting your own work or my work?
No answer.
The whole answer?
Yeah,
Why do you not like it?
because they're 2 different answers.
2 different answers. 1/2 tangent squared x plus c, 1/2 secant squared x plus c. That doesn't quite look the same, does it? What? Is there a moral or a lesson that we can learn here? Bethany?
I think they're actually equivalent expressions because if you use the rule that sine squared of x plus cosine squared of x equals 1, you can find that they're actually equivalent expressions and
Involving tangent squared and secant squared?
Yeah.
That is curious. So, hopefully everybody remembers the identity that sine squared x plus cosine squared x equals 1, owing to the fact that sine and cosine of x are always going to give you the x and y. Cosine and sine are going to give you the x and y coordinates of a point on the unit circle, x squared plus y squared equals 1. So, Bethany, how do we get from sine squared x plus cosine squared x equals 1 to saying something about secant squared and tangent squared?
So I first did the equivalent where I subtracted cosine squared of x from both sides.
That gives us sine squared x is 1 minus cosine squared x.
And then tangent squared of x can be written as sine of x over cosine of x squared.
Okay, so how do we get from,
Or just like using, because I'm trying to prove that 1/2 tangent squared of x equals the 1/2 secant squared of x plus c.
So yeah, I think from here we can actually get to saying something about secant and tangent if we, for instance, divide both sides by cosine squared x. Mary, what would we get if we took sine squared x divided by cosine squared x?
That'd be tan squared x.
Yeah, so that would be tangent squared x. Ty, how about 1 divided by cosine squared x?
That'd be 1 over secant squared, or that would just be secant squared x.
Yeah, 1 over cosine is equal to secant, so 1 over cosine squared would be secant squared x. And then, Carson, what would we get if we did cosine squared x divided by cosine squared x?
1.
No, that's just 1. So tangent squared x is equal to secant squared x minus 1. Okay, neat. So Bethany, you're saying you don't think we can use this somehow to say something about our two answers?
Yeah, so then we substitute secant squared x minus 1 into the expression 1/2 tangent squared of x plus c. And then that remaining negative 1/2 that gets, when we multiply all of it, just goes into the c because it's a constant.
I see. So if we substitute tangent squared with secant squared minus 1, that'll give us, what, 1/2 secant squared x minus 1/2 plus c. And what do we know about 1/2? Okay,
It's a constant.
it's a constant. So if we have one constant c, where c can be any constant at all, and we subtract 1/2, Emerson, what do we get if we take a constant and we subtract a constant?
A constant.
We're just going to get a constant, a different constant. But something that could be theoretically any constant nonetheless. So, turns out we actually did get the same answer. Yeah, very nice observation, Bethany. So, there is a moral to this story, and the moral to this story is if you integrate the same expression by different means, as long as you're doing everything correctly and on the books, you should always arrive at the same answer. Even if the answers don't necessarily look like they should be the same. Because 1/2 tangent squared x plus c, 1/2 secant squared x plus c. So I was walking around the room, to a lot of you all were like, I must have done something wrong if I'm getting 2 different answers. It's actually the same answer written 2 different ways. I could rewrite either answer to be 1/2 secant squared x plus some constant. Because tangent, with the idea being tangent squared and secant squared only are the same, other than one is a constant distance apart from the other. They're 1 apart from each other. So that distance of 1 apart from each other that they are, that can just get folded into the plus c term, since c can be any constant at all. There. So that was a bit of a sneaky one, but I liked it. Any questions or comments about either of these use subs? Ruby. So last thing from standard 2 I want to talk about is how do you handle a situation where you're taking a definite integral instead of an indefinite integral. integral from 0 to 1 of x times x squared minus 3 quantity squared. That is the one. That is the one that watch it, you. That is written in the packet because I changed this one up after I'd already printed my own copy of my notes. Originally, this was actually much more tedious. So this looks just like something we can do using any other U substitution problem. If I got rid of the 0 and the 1 and just said find the integral of x times x squared minus 3 quantity squared. So, question. If we ignore the fact that we're looking at a definite integral, meaning we're finding area from 0 to 1, how could we approach this as a U-sub problem if we were trying to find, say, antiderivatives of x times x squared minus 3 quantity squared? Anybody have an idea for something we could use for a choice of U here? James?
X squared minus 3 because it's an inside function.
Yeah, we have x squared minus 3 is an expression of x that we're then squaring. So I think x squared minus 3 is a good choice to try for a U sub. So let's let u be equal to x squared minus 3, which would give us du dx equals 2x. So du is equal to 2x dx. Notice we have x dx instead of 2x dx, so multiply both sides by a half, so that our x stuff, the x dx, can be written in terms of as an expression just in terms of u. So then from there, we could take our original integral and write it as the integral from 0 to 1 of what? 1/2 u squared du by replacing the x dx with 1/2 du, and this expression x squared minus 3 quantity squared we can just replace with u squared. So we get 1/2 u squared du integral from 0 to 1. Everyone all right with that? Aiden, you got some concerns?
Our values for inner integral that we're plugging in no longer are viable because we're using a different variable now?
Indeed. Yes. This is a pack of lies. It's close to correct, but we have a problem with this expression. Our problem is that all the variables that the expression that we're integrating is in terms of u. But our bounds, the 0 and the 1, those aren't u values, those are x values. So we can't just say, take the integral from 0 to 1 of 1/2 u squared du and say everything's all hunky-dory. So how can we get around this issue? The fact that we're integrating an expression that's in terms of u, but our two bounds that we're integrating between, that we're finding the area between, are x values rather than u values. James?
Should we just not account for that until we're completely done getting all the x's back?
Okay, so just leave the 0 and the 1 alone. Account for the fact that when we integrate 1/2 u squared, we'll get some expression in terms of u that we can then replace in terms of x.
Yeah.
That is certainly one option. So there's two options that we can do to actually approach this. Rhoda?
Wouldn't another option be to plug the bounds into what u equals and then solve for u and then use those as our bounds?
Convert 0 and 1 from x values to u values, in other words?
Yeah.
That would be the second option, yeah. So James and Rhoda have both given us approaches that should work out well for us to kind of get around this conundrum. Let's see. Rodham, I'm gonna go with your approach first. Then James, I'll talk through your approach and we'll see if we arrive at the same answer. Either way. So option 1, I'm not giving you credit for it, is to convert our bounds on the integral from x values to u values. So if we do that, we have two x bounds, x equals 0 and x equals 1. Rodham, how would you go about converting those from x values to u values?
You plug them into what we said u is, which is x squared minus 3.
Use the fact that u has to be equal to x squared minus 3? Yeah, so if x is 0, u would be 0 squared minus 3, which I think is just negative 3. And if x equals 1, we could say u is equal to 1 squared minus 3, which is negative 2. So instead of integrating from 0 to 1, we can instead integrate from negative 3 to negative 2. 1/2 u squared du. Where we've simply replaced 0 and 1, which are our x bounds, with negative 3 and negative 2, which are our u bounds. I bound, you bound. We all bounds for ice cream. Anyways. So now, both the expression we're integrating and our bounds are in terms of the variable u. So, Christopher, how would you integrate 1/2 u squared then with this in mind?
You would turn that into u cubed over 6.
Yeah, we'll get 1/2 times 1/3 u cubed, which simplifies to 1/6 u cubed. Which we need to evaluate from negative 3 to negative 2. Question. Before we plug in negative 3 and negative 2, do we need to convert 1/6 u cubed back into x's?
No.
Someone, who said no? Kate, why do you say no?
Because we've changed our bounds to be u values. If we change back to x, we'll change the bounds back to x as well.
Yeah, 1/6 u cubed is a u expression. Negative 3 and negative 2 are u bounds, bounds written in terms of the variable u. So it makes sense to plug in our u values for u rather than plugging them in for x. So if we do that, we'll get 1/6 times negative 2 cubed minus 1/6 times negative 3 cubed. And if we do that, we'll get negative 2 times negative 2 times negative 2. That's an odd number of negative. That's an odd number of negative, so it's negative. 2 cubed is 8. So we'll get negative 8/6 minus, well, actually it will become plus, because we'll get minus minus, 3 cubed. Hey, that's my favorite. That's 27. So we get negative 8/6 plus 27/6, which I believe is going to come out to 19/6. Or 3 1/6 if you prefer writing it as a mixed fraction. So, converted our x bounds to u bounds, and then plugged in the u bounds for u at this point. But otherwise, the integration process itself, we did the same u sub we would have if this had been an indefinite integral. The trickiness just came with plugging in our bounds at the very end. James, you had suggested something slightly different for how you would go about evaluating this integral. So, What was, can you remind us what was your idea?
Well, for getting a definite integral, you first get the indefinite integral, so you could just complete getting the indefinite integral first before thinking about the bounds, and then so you make sure you convert the u's back to x's, and then plug the bounds in.
Okay. So there is a second way to do this, which is to leave the bounds in terms of x. So this will be, I'll call this the option 2, the James option. Where option 2 is going to be leave the bounds in terms of x. Where we're still going to have 1/2 u squared is the expression we're trying to integrate with respect to u. But originally we had x bounds of x equals 0 and x equals 1. We don't just want to write 1 and 2 in, because if we write 1 and, or well, we definitely don't want 1 and 2, I don't know why I said 1 and 2. We don't want to just write 0 and 1 in, because that makes it look like 0 and 1 we're treating as u values. So if we want to just leave everything in terms of x, most common way to do that is to just make it clear, hey, this is from x equals 0 to x equals 1. Just accounting for the fact that the 0 and 1, these are not u values, these are x values, making it very abundantly clear what we're working with. And then from there, we can integrate. Christopher, you already did this over here, so we can just use that again. We'll get 1/6 u cubed evaluated from x equals 0 to x equals 1. Again, these are not u values, so we're just explicitly writing out that they're x values from x equals 0 to x equals 1, rather than from u equals 0 to u equals 1. U equals 1 is just bad grammar anyways. So, James, where do we go from here?
Then you plug the x squared minus 3 in for the u.
We get 1/6 times x squared minus 3 cubed, convert it back to x's, just like we would do if it was an indefinite integral. Except now, 0 and 1 are x values. Our expression's written in terms of x. We no longer need to write out the x equals 0 to x equals 1 because our bounds, 0 and 1, are written in terms of the same variable as the expression we're trying to integrate. And now we can just plug in 1 and 0 for x like we normally would if we had done a definite integral. Which would give us 1/6 times 1 squared minus 3 minus 1/6 times 0 squared minus 3, oops, forgot to cube. Which will give us 1/6 times 1 minus 3 is -2 cubed minus 1/6 times -3 cubed. Oh hey, we already know what that is. That comes out to that's going to come out to 19/6. Same answer as we got using Rodham's method, but we used a slightly different process to get there. Rodham's method converts the x bounds to u bounds, and then we can just plug in our u bounds here rather than having to convert 1/6 u cubed back in terms of x. James's work skips the step of having to convert 0 and 1 into u values, but then before we can plug 0 and 1 back in, we have to rewrite our expression in terms of x first. Anybody have a preferred method out of those two, do you think? I will say personally, my apologies to Rodham, I tend to go with James's method more. Like if you were to give me this out on the mean cold streets of Hillsdale, this is probably the way I would do it. Just keep everything in terms of x. But both of these methods are equally mathematically valid. They're always going to get you the same answer. The question basically becomes, do you want to convert 0 and the x bounds to u bounds here early on, or do you want to do it down here where we have to plug in 0 for x and hey, we get negative, we plug in 1 for x and get -2, we plug in 0 for x and get -3 down here. It's essentially the same steps, in other words, but in a slightly different order. But I don't care which one you use. I tend to use option 2, the James method myself, but if you prefer the Rotem method, by all means, don't let me stop you. Any questions or comments? Let's do another example. This so everybody's on the same page. Which piece do I want to do? Let's do this bottom one. This bottom one's a fun one. Let's integrate the function 1 over t natural log of t from t equals e to t equals e squared dt. Hee hee. Holy moly, how do we integrate this? This one's a little bit tricky, but it's a fun one. Does anybody see a choice of u that they would like to try in order to help us integrate this for our substitution? Katie?
ln of t.
Okay, so you want u to be equal to just plain old natural log of t? So what would that make our du dt?
Would it be, gosh. I don't remember the rule.
So how do we integrate natural log of t? Jonah?
1 over t?
Yeah, I've just come out to 1 over t. Derivative of natural log of x is just 1 over x, so same when you replace that with t's. Which will give us du is actually equal to 1 over t times dt. Is that helpful here? Roden?
Yeah. Because then you're able to use,
So how could we rewrite this then?
you could have it as 1, or it would just be u du.
I think it's going to be u, because that would be if we had natural log of t divided by t times dt. But we also have a natural log of t in our denominator. So we could rewrite this if we wanted to as 1 over t times 1 over natural log of t dt.
Oh, so it'd be 1 over u.
Yeah.
du.
This we could rewrite as 1 over u, and then the 1 over t and the dt we could combine into the du. So this is going to be an integral of 1 over u du, and I'm going to use the James method here from t equals e to t equals e squared. Excuse me. So how do we integrate 1 over u with respect to u? What function in terms of u, in other words, is going to have a derivative of 1 over u? John?
The natural log of the absolute value of u.
Yes, this is going to give us natural log of absolute value of u. We're doing a definite integral, so I'm going to leave off the plus c. Just say, take any antiderivative. For simplicity's sake, I'll choose the one that has a constant term of 0. From t equals e to t equals e squared. So if we convert that back into terms of from u's to t's, what does our natural log of absolute value of u become? James?
Natural log of absolute value of natural log of t.
Natural log of absolute value of natural log of t. Evaluated from e to e squared. Holy moly, a natural log inside of a natural log. Gadzooks. Well, this is going to end up being natural log of absolute value of natural log of e squared minus natural log of absolute value of natural log of e. Oh, jeepers creepers. Anybody know what natural log of e squared is? I'll give you a hint. Natural log of e squared is the same number, blank, that would make e to the power of that blank equal to e squared. So, Kate, what could we put in that blank there? Yeah. E squared obviously equals e squared. So the power of e that takes us to e squared, or natural log of e squared, is just going to be 2. So this ends up being natural log of absolute value of 2. How about natural log of e? So natural log of e is going to be the same blank. That'll make e to the power of that blank just equal to plain old vanilla e. So e to what power is going to give us e? 5? Yeah, just 1. So this will give us natural log of 2 minus natural log of 1. Excuse me, natural log of absolute value. Natural log of, well, we can simplify this. We can get rid of the absolute value because absolute value of 2 is just 2. What's natural log of 1? Well, e to what power is going to give us 1? Carson? Yeah, it's going to be 0. Anything to the 0th power, anything non-zero to the 0th power is going to give us 1. So natural log of 1 is just going to be 0. So our final answer, I think, is just going to be natural log of 2. And natural log of 2, I'm not going to repeat this trick with natural log of 2, because if I were to ask you e to what power gives us 2, there's not a nice answer for that. If we had used Rodham's method, what we would have gotten is we would have converted e and e squared to u values, and the u values we would have gotten would have just been 1 and 2, and then we'd have gotten natural log of 2 minus natural log of 1 in the same way. All right, that's it for standard 2. When we come back Friday, we're gonna do a quiz over u sub. You could probably expect 1 indefinite and 1 definite integral, hint, hint. And then from there, we're going to go into our next integration technique, which is integration by parts. Hope you all have a good one. See y'all on Friday. Again, don't forget office hours today are canceled. Tomorrow, I'll have an extra hour and a half of office hour in the morning from 10 to 11.
Thank you.
Thank you, Kip.